All right, so now that you've written down this problem and seen the formula into the notes, written it into your notes here that we're going to be using, now let's actually apply that formula to this particular problem. So we're putting $500 into a savings account that pays 0.25 annual interest. How much will be in the account after 8 years? And so notice there's two parts. First up, we got to just write the equation. So let's go ahead and write our equation here. Let's see here. So do we know what A is? No. A, as we just saw in our notes, stands for the amount. That is the final amount. That's what we're trying to figure out. What amount will we end up with? So that's just going to stay in A. And then it's going to be A of T. So A, we don't know. T, do we know what T equals?
Yes.
Yes, we do. That is going to be 8 years. So wherever I see T, I'm going to put in an 8. Equals. The next thing is the P value. What's the value of P in this equation? Or this situation?
500.
Should be the 500, yes. P is principal. That's just financial language for starting amount. So we're going to go 500, then parentheses, 1 plus. It's always 1 plus. That never changes there. And then R. What is R here? Well, if anything's going to throw you off, it's probably this part right here. Because R is 0.25%. But anytime we calculate with a percent, we don't leave it as a percent. We have to turn that percent into a decimal. And so, do you remember how to turn the percent into a decimal?
Yeah.
Remember, I take the percent and I divide it by 100? Or some of you remember it as you move the decimal over 2 places. And so that's going to give us here 0.0025. That's the actual R value that we're going to use here, is 0.0025. Then that's to the power of T. Remember, we already figured out what T was back here. T was 8. So this is our actual equation that we're going to be using then. All right, now I want to make sure that you actually can calculate this value out correctly, so it's going to be a little bit of calculator work. First thing though, always order of operations says do the stuff inside the parentheses. So go ahead and just do that addition right away. Make that into a 1.0025, and then order of operations from there says do the exponent, and then do the multiplication. When you do that calculation, you should be getting an answer of 510.09, so $510.09. Notice in this problem I did not tell you what to round to, but I would expect you to know. Because we're talking about money here, and anytime you talk about money, you should always round to the cent. That is, to the hundredth place. All right, so there's our final answer for that. And yes, the beautiful thing about this work that we're doing here in this equation is that this is actual, real-life, useful kind of information. If you put $500 in a savings account that pays 0.25 interest, 0.25% interest, that's what you would get after 8 years. You didn't exactly get a lot of return out after 8 years, did you? You made a whole $10 for leaving them to manage your 500. That's pretty typical of a savings account. A savings account is not there so that you can grow your money. A savings account is there just so you can put it someplace safe while you wait to use it. Investing is a whole separate kind of thing. And we'll actually take a look at an investment here in a minute and see what kind of returns those get. But this shows why we don't put it into a savings account as an investment, because it's not really going to grow. In fact, if we want to get really technical, you're technically really losing money if you compare it to inflation. Okay. Now, I'm going to springboard off of that problem here so we can see what happens in this situation. Suppose your account decreased in value by 0.25% each year. Okay, first of all, if you put money in a bank and they take away a certain percent of your account every year, find a new bank, okay? That's not really going to happen. But I needed an example to be able to show what does happen when it goes down each year. So we want to write an equation for this situation and see what happens in this kind of a case. What you'll find is that the equation is actually extraordinarily similar to our original here. except we got to make one little change. We're now decreasing by 0.25%. Basically, what that means is that it's like our rate is a negative. And so I end up doing plus a negative 0.0025 when I go down in value. Or if you want to make your life a little easier on the calculation, that just means we're doing 1 minus that percent. And so, once again, with that in mind, go ahead and calculate the value. What would this give us in 8 years? All right, and for that calculation, you hopefully got an answer of $490.09. One little side note here. Notice that when it was increasing in value, we gained $10.09. When we were decreasing in value, we actually went down $9.91. So notice it's not the exact same amount that we go up as what we would go down. So they're actually totally separate calculations. It's the whole idea about the fact that we're compounding on the interest. So that percent is taken of the new value each year. An idea we can get into a little bit more in a bit. All right, now we're going to take a look at an investing problem. So in this case, when you turn 18, your aunt gives you $1,000 in a retirement account. It's good to have an aunt like that, right? If that investment averages 11% a year, how much money will you have if you want to retire at age 60? Now we're going to end up using the same equation here. How do I know? Because that equation on compounding interest is used anytime we're going up or down by a given percent each year, month, day, whatever it is. So anytime you're increasing and decreasing by a percent, that's our equation. All right. So then let's go ahead and set up our equation here and see what it would look like. All right, so for writing this equation, it's going to be A of t again. I'm going to come back to the t here in a minute. Equals P, my starting amount, my principal is 1,000, times 1 plus R. Remember, R comes from the percent, but always turn the percent into a decimal. So take the percent, divide it by 100. 11 divided by 100 is 0.11 to the power of t. Now the t here is not 18 and it's not 60. Remember, the t is the amount of time that it's left to grow. If we get it at 18 and we want it to be in there until we're 60, I have to do the 60 minus 18, which gives us 42. So that's what we're going to plug in for t anywhere where t appears. And now that we have our equation, now we can go ahead and find out what that value would be. This is an investment situation. We put the money into the retirement account because we're going to leave it there. We're investing it so that it will grow over time and become something much bigger for when we actually need it. Let's see what that gives us. When you do that calculation, you should be finding that it ends up being worth $80,000. Yes, these are real numbers, and this is what would really happen. If you just start with $1,000 and just leave it in there at 11% a year, in 42 years, that $1,000 is now $80,000. Not bad. Now, there is one caveat to this, so a little bit of real-world insight when it comes to investing in retirement accounts, stuff like that. You notice the one thing that we have to do in order to be able to pull this off is we have to put the $1,000 in there, and we have to leave it there. If you put the $1,000 in the retirement account or in any other investment, and then you decide a little later, hey, I'd like to get a car, or whatever it is that's of interest at that moment, and you pull it out, it's not going to hit 80,000 or anything else because it's just whatever it is at that moment that you pull it out. So you want to leave it there until you retire. People will often give the advice as a result saying the ideal way to invest is you put the money in and then you forget it's there so you're not tempted to use it. Now, just to show kind of the power that time has in this kind of a thing, I want to look at one other little variation here. What if this gift that our aunt gave us were given to us when we were born instead of when we turned 18? And we still want to retire when we turn 60. What's it going to be worth in that case? So notice the only real difference between this situation and the last one is that in the last situation it was 42 years, and this one it's for the full 60 years that it's going to be left in there. Alright, so what does that give us? Well, after 42 years, our money grew to be 80 times what it originally was. That was after 42 years. Just another 18 years in the whole situation, and now all of a sudden it's worth over 500 times as much as the original amount was. When people talk about the power of compounding interest, this is what they're talking about. The longer you leave the money in there, and the higher the rate is you get out of it, the bigger this number grows over time. The trick though is, again, remember, you got to leave it there. As soon as you pull it out, it stops growing.